95% of the universe does not exist, at least not in any way you can see, touch, or measure with any instrument you have ever heard of. Every star you have ever looked at, every galaxy, every planet, every atom in your body, all of it combined, makes up just 5% of what is actually out there. The other 95% is something else entirely, something invisible, something that has no name that satisfies scientists, something that broke every rule physics thought it had figured out. And one woman, one single woman, is the reason we know this. Her name was Vera Rubin, and what she found changed the entire story of what the universe actually is. Let's start at the beginning. Not Vera's beginning, the universe's beginning. When the Big Bang happened and something went wrong. Or maybe something went exactly right and we just can't figure out what it was. The matter that formed, the stars, the gas clouds, the building blocks of galaxies, didn't behave the way it should. Galaxies formed too fast. They held together too tightly. The math didn't add up. For decades, scientists noticed the problem and quietly moved on because they had no explanation. Then Vera came along, and she didn't move on. She stared at the problem until it confessed. Born in 1928 in Philadelphia, Vera Rubin developed an early fascination with the night sky, encouraged by her father. As a teenager, she spent countless evenings tracking the movement of stars using a homemade telescope she built herself. This wasn't a girl playing pretend scientist. This was a human being who looked up and felt something calling her. Most people look at the night sky and feel wonder. Vera looked at it and felt questions, hundreds of them. Questions that wouldn't let her sleep. She was the only astronomy major to graduate from Vassar College in New York in 1948. When she was told women weren't allowed to enroll in Princeton's graduate astronomy program, she earned a master's degree from Cornell University instead. Think about that for a second. Princeton said no, not because she wasn't brilliant enough, not because her scores weren't good enough, but because of her gender. A policy that, by the way, wouldn't change until 1975. So she went around them. She went to Cornell, then to Georgetown, finished her PhD, and kept going. Every door they closed, she found a window. For her doctoral thesis at Georgetown University, Rubin studied the distribution of galaxies in space. Arrangements with her doctoral supervisor were challenging. His office was located in a part of the campus where women weren't allowed. Despite these obstacles, Rubin persevered and made a key discovery. Galaxies are not distributed evenly through space, but tend to gather in clusters. She submitted her findings for publication. And what happened? The editor of the most respected astrophysics journal at the time rejected her paper. Not because it was wrong, but because his own student was working on the same topic. A woman's original research, buried under office politics. She kept going anyway. Now, here is where the story gets truly extraordinary. By the 1960s, Vera was working at the Carnegie Institution in Washington, and she made a decision that would quietly rewrite the laws of physics. She began studying spiral galaxies, specifically how fast they spin. Now, this sounds straightforward, but it had enormous implications. See, when you look at our solar system, the planets closest to the sun move the fastest. Mercury zips around the sun at incredible speed. Neptune, out at the edge, moves much more slowly. This is basic physics, going back to Kepler and Newton. The further you are from the center of mass, the slower you move. Everyone knew this. It was settled science. It was obvious. In 1965, Rubin broke new ground by becoming the first woman to work at the Mount Palomar Observatory, collaborating with astronomer Kent Ford from the Carnegie Institution. Together, they began studying the rotational speeds of spiral galaxies. By measuring how fast stars moved at varying distances from the galactic center, they uncovered something unexpected. Stars located far from the center were rotating just as quickly, or even faster, than those closer in. According to existing theories, this should not have been possible. Let that sink in. The stars at the very edges of these galaxies, the stars that should be crawling along like Neptune creeping around the sun, they were screaming around at the same speed as the stars right at the center. This is like if you watched a spinning record and every single point on the record, from the center hole all the way to the outer edge, was moving at exactly the same speed. It is physically impossible, unless there is something else there, something invisible, something massive, something exerting gravitational pull that isn't showing up on any telescope. While the explanation for that strange behavior didn't become clear to Rubin until 2 years later, these printouts represented the first direct evidence of dark matter. Scientists now know that dark matter comprises some 84% of the universe's material. Its invisible particles swarm and stream and slam through the whole cosmos. It affects how stars move within galaxies, how galaxies tug on each other, and how all that matter clumped together in the first place. It is to the cosmos like air is to humans, ubiquitous, necessary, unseen, but felt. Dark matter. She didn't name it that. The term already existed. floated around at the fringes by a few scientists over the decades. But Vera Rubin is the one who proved it was real. She measured galaxy after galaxy after galaxy, 60 spiral galaxies. Every single one showed the same result. Flat rotation curves, scientists call it now. The speed doesn't drop off at the edges, it stays flat. And the only explanation, the only one that works mathematically, is that every single galaxy is surrounded by a massive invisible halo of matter that we cannot see, cannot detect directly, but that has been bending the rules of gravity this entire time. The research showed there is 10 times as much dark matter as visible material in a galaxy. Thanks to the discovery, physicists now know 90% of the universe is made of dark material. Read that again. 10 times more dark matter than visible matter in every galaxy. Every galaxy you have ever seen in a photograph, the Milky Way, Andromeda, every spiral and elliptical, it's like an iceberg. What you see is the tip. The vast invisible bulk underneath is dark matter. Now, let's zoom out even further because the numbers get even more staggering. Scientists estimate that ordinary matter makes up only about 5% of the universe, while dark matter makes up about 27%. The rest is thought to be dark energy, which is its own mystery. 5%. Everything you have ever seen, everything that has ever been photographed through every telescope ever built, every atom of every person who has ever lived, 5%. The universe is mostly something else, something we still cannot explain. And Vera Rubin found it in data, in printouts, in numbers that didn't add up the way they were supposed to. She sat in observatories staring at the math. And instead of saying, there must be an error, she said, what if the math is right and our understanding is wrong? That is the move that separates a good scientist from a great one. The willingness to trust the data over the assumption. But here's the part of this story that will haunt you. The part that says something deeply uncomfortable about how the world treats people who break through barriers they were never supposed to cross. Dark matter is one of the most important discoveries in the history of astronomy. And many scientists believed Vera Rubin deserved a Nobel Prize for revealing it, yet the prize never came. She died on December 25, 2016, at the age of 88, without receiving the field's highest honor, a mission that many in the scientific community regard as a glaring injustice. Emily Levesque, an astronomer at the University of Washington, says, the existence of dark matter has utterly revolutionized our concept of the universe and our entire field. The ongoing effort to understand the role of dark matter has basically spawned entire subfields within astrophysics and particle physics. At this point, Alfred Nobel's will describes the physics prize as recognizing the most important discovery within the field of physics. If dark matter doesn't fit that description, I don't know what does. No woman had received the Nobel Prize in Physics since 1963. Vera Rubin never got one. She received the National Medal of Science. She received the Gold Medal of the Royal Astronomical Society. She received the Gruber Prize in Cosmology. She was elected to the National Academy of Sciences, only the second female astronomer to ever receive that honor. But the Nobel, the one prize the entire world recognizes, denied her. Not because the discovery wasn't big enough, it was the biggest. Denied because of a system that didn't see her fully. Rubin herself was characteristically gracious about it, focusing on the science rather than the accolades. Fame is fleeting, she once remarked. My numbers mean more to me than my name. That line, that single line, tells you everything about who Vera Rubin was. She did not discover dark matter for the recognition. She discovered it because the universe was lying to everyone, and she refused to let it. Now, here is where this story reaches into the present, because Vera Rubin's work didn't end when she died. It is only now, right now in 2026, that the full scale of her legacy is beginning to unfold, and it is enormous. In 2019, the Large Synoptic Survey Telescope, designed to map the universe in greater detail than ever before, was renamed the Vera C. Rubin Observatory. This observatory, the first U.S. national observatory named after a woman, will carry Rubin's legacy forward by mapping dark matter across the universe. The first national observatory in American history named after a woman, and it carries her name because no name fits better. On June 30th, 2026, the NSF DOE Rubin Observatory officially began the Revolutionary Legacy Survey of Space and Time, known as the LSST. The 10-year survey is Rubin's signature campaign to create the most comprehensive cinematic record of the universe in history. Think about what that means. A 10-year mission, a single telescope, scanning the entire southern hemisphere, sky over and over every night for a decade. Using the largest camera ever built, the Rubin Observatory will repeatedly scan the sky for 10 years to create an ultra-wide, ultra-high-definition cosmic movie. It is named after astronomer Vera Rubin, who provided the first convincing evidence for the existence of dark matter. The largest camera ever built for astronomy, 3.2 gigapixels. To put that in perspective, your phone camera might be 12 megapixels. This camera is 3,200 megapixels. It can capture a patch of sky the size of 40 full moons in a single image. Every night, it sends out approximately 7 million alerts, 7 million about new cosmic events detected in the previous 24 hours. Rubin Observatory's LSST launched June 30th, 2026, unleashing a nightly 7 million alert sky survey powered by a 60-second alert pipeline that will produce the first high-precision, independent test of whether dark energy is a fixed cosmological constant or has evolved. Dark energy, not dark matter, dark energy, that other mystery, the one that makes up 68% of the universe, the force that is actively pushing the universe apart, accelerating its expansion in defiance of gravity. Scientists have been arguing for years about whether dark energy is constant, Einstein's cosmological constant, or whether it has been changing over time. Because if it's changing, then every model of the universe we have built is wrong. The standard model of cosmology, the foundational theory of how everything works at the largest scales, potentially wrong. And the Rubin Observatory is the instrument that will finally tell us. With images taken through 6 different color filters mounted to the largest camera ever built for astronomy and astrophysics, the Vera Rubin Observatory's upcoming legacy survey of space and time will reveal never-before-seen stellar streams around the Milky Way and the telltale effects of their interactions with dark matter. Stellar streams? These are rivers of stars, the ghost trails of galaxies that got pulled apart by gravity billions of years ago. They stretch across the sky like glittering threads, and they are incredibly sensitive to tiny gravitational nudges. If dark matter is clumped in certain places, it leaves a fingerprint in these streams, a distortion, a gap, a kink in the line. And now, for the first time, we have a telescope powerful enough to read those fingerprints in detail. The Rubin Observatory's mission is expected to yield a staggering number of new discoveries. Over 17 billion Milky Way stars, about 20 billion galaxies, and around 10 million supernovas, over 1,000 per night, plus a slew of comparatively nearby objects in our own solar system. 17 billion stars in the Milky Way cataloged, 20 billion galaxies, 10 million exploding stars tracked over the decade. Every night, more than 1,000 supernovas logged, analyzed, their light curves measured. This is not science fiction. This is happening right now. The data is flowing, the discoveries are beginning. Scientists at Johns Hopkins may be closing in on dark matter's elusive trail, uncovering a mysterious gamma-ray glow at the heart of our galaxy that could signal unseen matter colliding, dark matter annihilating itself. 2 particles of dark matter slamming into each other at the galactic center and releasing a burst of gamma rays. If this signal holds up, if it is confirmed, it would be the first time in history that human beings have directly detected dark matter doing something observable. Not just measuring its gravitational effects, but catching it in the act. Scientists may finally be catching a glimpse of dark matter. The LZ Zeppelin detector is breaking new ground in the hunt for dark matter, setting unprecedented limits on WIMP particles. Its results not only narrow the possibilities for dark matter, but also open new territory for exploration. WIMPs, weakly interacting massive particles, the leading candidate for what dark matter actually is. WIMPs are hypothetical particles that interact through gravity and the weak nuclear force, making them incredibly hard to detect. Experiments like Supersede EMS and Tesseract use ultra-sensitive detectors cooled to near absolute zero to catch rare interactions between WIMPs and ordinary matter. These detectors sit deep underground, thousands of meters of rock shielding them from cosmic rays, waiting for a dark matter particle to brush against an ordinary atom. One interaction? Just one. That's all they need to confirm the most important discovery in physics since the atom. Scientists now think dark matter might come in 2 forms. 2 types of dark matter, not one. Not a single mysterious particle, but possibly a whole dark sector. A shadowy universe of particles that interact with each other through forces we haven't detected yet, that exist all around us right now, passing through your hand, through this planet, through the entire solar system without leaving a trace. A parallel physics happening everywhere, invisible to everything we have built. And now there's another instrument entering the picture. By the late 2020s, Rubin and the Nancy Grace Roman Space Telescope, launching August 30th, 2026, will together produce the datasets needed to settle the question of dark energy definitively. 2 observatories working together, one on the ground, one in space, combining their data to answer the question that has been sitting at the center of cosmology for 20 years. Is dark energy changing? Is the universe's fate different from what we thought? An international research collaboration has used advanced computer simulations to investigate how faint radio signals from the early universe, soon to be observed from missions on the far side of the moon, could shed light on the fundamental properties of dark matter. The far side of the moon. We are putting radio telescopes on the far side of the moon specifically to listen for the whisper of dark matter in signals from the very beginning of time. The first light, after the Big Bang, a period called the Cosmic Dark Ages, might contain the fingerprint of how dark matter behaved when the universe was young. And if we can read that fingerprint, we might finally understand what it is. As Rubin once wrote, "Still more mysteries of the universe remain hidden. Their discovery awaits the adventurous scientists of the future." She wrote those words, and she had no idea that the adventurous scientists of the future would be using an observatory built in her honor, carrying her name on the side of an 8.4-meter telescope on a mountaintop in Chile, pointed at the sky every night, scanning billions of galaxies, looking for the very thing she spent her life proving exists. She had no idea her name would be stamped on the greatest dark matter hunting instrument in human history. She just did the work. She just trusted the numbers. She just refused to stop. Here's what we know right now. As of today in 2026, about 95% of the so-called known universe is a total mystery. We have no clue what it is, except that it's weirdly different from any sort of matter or energy humans actually know anything about. The stuff we do know about makes up a scant 5% of the universe. Vera Rubin found the first crack in the wall between what we understood and what is actually out there. She did it with data and stubbornness and a willingness to believe the universe over the textbook. She got denied admission to Princeton because she was a woman. She got her research buried by an editor protecting his student. She watched men receive Nobel Prizes for discoveries she considered less significant than hers. And she kept going. For 50 years, she kept going. In 2025, the United States Mint released a Vera Rubin quarter as the 18th coin in the American Women Quarters program, recognizing her as a trailblazing astronomer whose groundbreaking research provided crucial evidence for the existence of dark matter. Her face on American currency, because a homemade cardboard telescope pointed at stars from a bedroom window in Philadelphia in the 1930s, eventually changed everything we thought we knew about the structure of the universe itself. The Rubin Observatory began its 10-year mission on June 30th, 2026. Every night it scans. Every night it sends 7 million alerts. Every night it collects data that will take scientists decades to fully analyze. And somewhere in that data, in the light curves of distant supernovas, in the shapes of galaxies distorted by invisible mass, in the gaps carved through stellar streams by dark matter halos we cannot see, somewhere in all of that is the answer to the question Vera Rubin first asked: what is the invisible thing holding everything together? We don't know yet, but we are closer than we have ever been. And we are only here because one woman refused to accept that the universe was allowed to keep secrets just because the numbers were inconvenient. The most powerful telescope in history bears her name. The most important astronomical survey in history is running right now because of what she found. And the mystery she cracked open, the one that showed us the universe is mostly something we cannot see, that mystery is still the deepest, most important scientific question of our time. 95% unknown. One woman who changed what we know about the 5%. And a machine named after her that may finally tell us what the rest of it is. The universe has been hiding something for 14 billion years. Vera Rubin was the first person to prove it.